Greetings and welcome, friends. Yesterday we talked about properties of parallelograms. But what if I tried to turn that around? What if I had a quadrilateral that had certain properties, but I wanted to determine whether or not it was a parallelogram? And so enter some of these converses, where some of the converse statements from yesterday happen to be true. And then some other theorems will exist in which I'll be able to prove a particular quadrilateral is a parallelogram based on the limited starter information that I have. So it turns out that here's two new theorems for us. Even though they're called converses, they're still theorems, just converses of other theorems. It says that if both pairs of opposite sides of a quadrilad are congruent, then the quadrilateral is a parallelogram. Remember back in the day when we would prove angle properties regarding parallel lines cut by a transversal? The converses of those statements, like corresponding angles converse, alternate interior angles converse, those were used to prove lines parallel, not prove something about the angles, right? Same thing here. We are using these converses to prove a quadrilateral is a parallelogram, not to come to a conclusion about its properties that it might have. So opposite sides turns out is sufficient information to prove that this is a parallelogram. Also happens to be true, opposite angles are sufficient. If I know that both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Okay, let's see if we can actually, let's prove one of these here. Because, yeah, I mean, you might, feel like it's true, but we gotta know that it's true. Man, good at that. So, here we go. Statement, reason. I'm so glad I have already printed out this for you guys, so you can just, not have to draw pictures, right, Ryan? That's right. So here I've got my parallelogram. Well, actually I lied. A quadrilateral is my given information, in which, some opposite sides are congruent, both pairs. What's something I could do to prove this is a parallelogram? By the way, the only way I would have to do that is I've got to show that the opposite sides are parallel. And then by definition of a parallelogram, I could do that. What route do you think I could take? This is actually a cool combination of almost all of our skills so far. Yeah, that was some of the given information. Yeah. No worries. Yeah, AC is congruent to itself. You could write that as CA or AC. Okay. All right, so this is true by reflexive. And then what are you saying is true by side, side, side? Whoa, whoa, slow down. Whoa, so you're saying that triangle ABC is congruent to who now? Well, I went from A to B, so I'll have to go from C to D first to match up that. So CDA. Okay, by side, 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 right? So we showed this. So I could show that some of these angles. Well, I already knew that. Well, wait, I don't know that that's parallel yet. No, we don't know that. All right, so CPCTC could tell me some properties about these angles. Here's one of the things that I could say. I'll call that, I'm trying to prove it's a parallelogram, not that it's congruent. No, that's where I'm going. So angle BAC is congruent to angle DCA. by CPCTC. I also could similarly say that this angle is going to be congruent to that angle. So that's DAC congruent to angle BCA for the same reason, CPCTC. How is that going to help me prove parallel sides? Yeah, alternate interior angles converse. All right, these two angles are alternate interior angles to each other with respect to these cut by the transversal diagonal that we drew. And since they are congruent then by the converse, I can say that these are now parallel. That's one pair of parallel sides. And then for very similar reasons, I could say BC is parallel to AD. All right. And then lastly, I could say that ABCD is a parallelogram. Parallelo. And that is by def of parallelo. Right? A parallelogram is a quadrilateral that has opposite sides parallel. What if it was like a kite, though? That's two congruent triangles. That's a non-parallelogram. You might be able to, like, you could kind of come up with write a theorem that if you have two congruent triangles attached at a common side that are like flipped of each other, though. Yeah, you could kind of come up with your own thoughts. I see where you're going. So let's take a look at example 1. Whee! Wow, this is fun. An amusement park ride has a moving platform attached to 4 swinging arms. The platform swings back and forth higher and higher until it goes to the top and around in a circular motion. The diagram below, in the diagram below, AD and BC represent 2 of the swinging arms. Those appear to be congruent by def of Kong since their measures are equal. Let's see, and DC is parallel to the ground. Interesting. Parallel to the ground. I didn't see them going there. Explain why moving platform AB is always parallel to the ground. Okay. Well, I could say that AD is congruent to BC by def of Kong. Yeah, so I guess I could kind of do statement reason sort of thing. So yeah, my given information is this parallel fact and the side measures being equal. So yeah, I could say that AD is congruent to BC by def of Kong. For the same reason, I could say AB is congruent to CD, right? That's these two, by def of Kong. I could then show that ABCD is a parallelogram. Here's my hieroglyphics version of parallelogram. Why is that a parallelogram? Parallelogram, opposite sides converse. So if this is a parallelogram, then I could say that AB is parallel to what? Not yet. AB is the top. Yeah, DC or CD, whichever. By def of parallelogram. And then, wasn't there like a transitive property of parallel lines or something? Actually, that's literally what it's called. So I could say that AB is parallel to L. That's called the transprop of, I'll just write symbol, parallel lines. Bam! Like it. Excellent, excellent, excellent. See. Yeah, so we can now prove things or parallelograms and then put those facts to use. Example 2 is a little less interesting, a little too similar to yesterday's problems. It says, for which values of x and y is this going to be a parallelogram? And so this is only going to be a parallelogram if opposite sides are congruent. Right, and then I will go through and kind of see what I can do from there. So what's a statement that would help me to find some... Oh, you've got some solutions already? Why did you choose to compare these two first? Because they're congruent. And I chose those two statements first because these two statements have two variables in them, and so it's a little less helpful. I can more quickly find the value of a variable this way. And then, yeah, y is going to equal x plus 7, which is 17. And so only for these values of x and y could we conclude that this is a parallelogram. All right, it turns out that there's some other theorems, means in which we can prove quadrilaterals or parallelograms. Opposite sides parallel and congruent. The key here is if I have one pair, exactly one pair of sides that are parallel and congruent, it turns out that's sufficient information to prove that it's a parallelogram. I think I've got this partially set up in Geometer Sketchpad for us. What I've done here is I created a segment and then a point and a parallel line through that point that's parallel to that segment. And then I measured the distance of that segment using my compass tool, and I'm going to now connect the dots. All right. So these starting segments are going to always have been parallel, because that's how I define them, and they are congruent to each other. And the question is the remaining shape always going to be a parallelogram? And it turns out it is. There's no way that I can not make that a parallelogram. All right, so that's almost rectangular there. So that's kind of an interesting result. Parallel and congruent, one pair only. It turns out that the other pair of sides will also be parallel. It'll be a parallelogram, and then all of the properties of parallelograms will apply. All right, and then there's also this parallelogram diagonals converse, that if the diagonals of any quadrilateral bisect each other, then the quadrilateral is a parallelogram. Right, so that's a converse of a theorem from yesterday. Theorem 7.9, this was not a property from yesterday. This was not a theorem from yesterday, and therefore it is not a converse of one of those. Let's take a look at example 3 with this charming little door found in Harry Potterville, whatever that's called. I don't know. Someone told me the name of that village that he goes to. I have no idea. I don't know. I'm not a Potter. Well, or maybe he should be hired. Because the doorway shown is part of a building in England, and over time, the building has leaned sideways. I don't know. So when they had to rebuild a door, they had to cut it into an interesting shape. Explain how you know that SV is equal to TU. So SV, TU. What could I say? So that's parallelogram, opposite side, parallel, and congruent theorem. Man, that's not a great one. Ooh, it looks like prospect. Okay. Yeah, so opposite sides, parallel, and congruent theorem. Opposite sides, parallel, and congruent theorem. Sure. All right, so it's a parallelogram. How does that help me? And why is this true? No. Definition of parallelogram would allow me to show they're parallel. Gentlemen? So why is this true? No, that's for triangles. What allows me to say that the opposite sides of a parallelogram are congruent? The parallelogram opposite sides congruence theorem. All right, once I already know this is a parallelogram, now the properties from yesterday apply. And then because those are equal, I could say that their measures are, or because they're congruent, sorry, their measures are equal by def of Kong. There you go. So if you're the carpenter who has to build a new door, now you are able. The house, yeah, the house is tilted, then they had to build a door to match it. Maybe. Huh. You could, with some engineering, you could figure out, you know, whether or not it's strong enough to stay up. What if they built like a beam on the other side that the house is leaning against so it's not going to topple? Oh, maybe. Yeah, you'd have to know the tensile strength of all of the components of the house and whether or not it, yeah. Example 4, finding diagonal lengths of a parallelogram. For what values of x is this a parallelogram? Well, this quadrilateral is a parallelogram anytime its diagonals bisect each other. So that would be, these ones are kind of simple. I could probably hand this to an Algebra 1 student and they would just assume you set those two equal, but they wouldn't really know that this was true. They wouldn't really know. Subtract 5x from both sides, divide both sides by -2, x equals 4. Bam, not bad. Now, it turns out you can also do, actually, oh, this is a really good thing to look at. You can also prove on a coordinate plane when a figure, a quadrilateral, is a parallelogram. And check this out. Here's a summary of all of these things. I can prove a quadrilateral is a parallelogram by definition, by the opposite sides converse, opposite angles converse, opposite sides parallel and congruent theorem, and the diagonals converse. Now, if I gave you the coordinates of 4 points on a coordinate plane, how could I use points on a plane to show that the opposite sides are parallel? I'd need to use the slope formula. Formula, there we go. Do you guys remember the slope formula? y2 rise over 1, or y2 minus y1 over x2 minus x1 is equal to the slope. I want to point out you'd have to use this formula 4 times. 4 times. Okay? 4 times. Bam. All right, if I wanted to show opposite sides were congruent, what could I do on a coordinate plane? 4 times the distance formula. Right, Ryan? And let's see, Liam and Ryan, if I can get the distance formula right. D is equal to the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. There's the slow clap I've been working for. And you would have to do distance formula 4 times, and then through logic of def of Kong, you could then prove that this is a parallelogram by the parallelogram opposite sides converse. All right. This one, we actually couldn't necessarily really put to use on a coordinate plane until I taught you some trigonometry. Yeah. Because you guys can't find angles between lines on a coordinate plane just yet, right? Ryan, your phone's telling you the same thing, right? It's true. So this actually wouldn't help me on a coordinate plane. What could I do for problem for 4 if I was trying to prove 2 times distance and 2 times slope? And then check this out. The best way to show a quadrilateral on the coordinate plane is a parallelogram is using method number 5. What could I do here? I could do distance here, distance here, distance here, distance here. What's a faster way? Yeah, the midpoint formula. And check this out. I only have to do this twice instead of a total of 4, right? So 2 times instead of 4 times. The midpoint formula, by the way, is the average of the x's will give you the x coordinate of the midpoint, and the average of the y's will give you the y coordinate of the midpoint. And if both midpoints are the same point, then the diagonals bisect each other, and then it's a parallelogram by the parallelogram diagonals converse. So if you have a choice, this is the fastest way to do it because you only have to do 2 formulas rather than 4. I'm going to end right there. I'll let you guys figure out how to do that type of problem on your own. Have a great day. Bye-bye.